Figure below shows a U-tube with a uniform inner radius. The tube is open at the right limb and is closed at the left limb. Mercury contained in the tube traps a H1 cm air columns at the left limb. Mercury level at the right limb is half H1 cm above the valve. Through the valve, certain amount of air is released, and that makes the mercury level at the right limb is now at the same height as for the valve. Find the ratio of the mass of air in the air columns in terms of H1 and H before and after the valve being open. Assumes that the atmospheric pressure is ρgh and the temperature is unchanged. This is the valve. Before the valve is open, the air columns at the left limbs has a length H1, and at the right limbs, the mercury above the valve is H1 over 2 cm. After the valve is open and release some air from the air columns, and of course after that the valve will close again, the length of the air columns now reduced to half H1 cm, and at the right limbs the mercury level now is at the same height as for this valve. Since this part of the mercury is not flowing, then we know that the pressure act on A and the pressure act on B downwards must be the same. The pressure act on A downwards is come from the pressure of the air in the air columns, and the pressure act on the B downwards is due to the atmospheric pressure and the pressure due to the mercury columns with the length H1 over 2 cm plus the mercury pressure with the length of H1 cm. Now we assume that the air in the air column is an ideal gas, and we apply the equations of the states to the ideal gas. Then the P here should be the pressure of the gas, and this pressure of the gas should be the pressure act on this mercury level. And this pressure is, as we mentioned just now, it is the same as the pressure at the B. And the pressure at the B can be written down as the summations of three terms. One is due to the atmospheric pressure, which is ρgh. And the second one is the half ρg times the half of the H1 cm. So we have the second terms. And the third one is the pressure due to the mercury columns with this length, which is ρgh1. So this P now is pressure, which is the same as the pressure of the gas in the air columns that act on A. And the V is the air columns, which is equal to the S times H1, where the S is the cross-sectional area of the U-tips, and the H1 is the length of these air columns, equal to M over M. This N now changes to M over M. M is the mass of the air molecule in the air columns. M is the molar mass of the gas or the air in the air columns, and R is the gas constant. T is the temperature in Kelvin of the gas. So now we can factorize the ρg in the bracket. Then the bracket now, the things in the bracket now remains H plus H1 over 2 plus the H1 and times ρg as H1 equal to M over M RT. Now these equations, we name it as the equations number 1. This is for the equation of state for the air columns in the left limbs of the U-tips before the valve is opened. Now we apply the same analysis to the air columns at the left limbs after the valve is opened to release some air molecule. Now, of course, after release the air molecule, then this valve have to close again. And the pressure at the C now is the same as the pressure at the D. And the length of the air columns now reduced to half of the H1. Therefore, since the pressure at C and D is the same, so now we can write down the pressure as the at the D is rho GH due to the atmospheric pressure plus rho G half of the H1 due to the mercury columns that act on D. This is the pressure act on D, but it will be the same as the pressure act on C, which is also equal to the pressure of the gas at in the air columns. So and it is equal to right hand side is m prime over mRT. M now you see the m now changed to m prime because the mass of the air molecule in the air columns now is already changed, and we know that m1 should be smaller than m. The capital M is the molar mass, which is the same for the two cases because it refers to the same types of the air in the air columns, and it is times RT. So this whole expression actually again it is come from the PV equal to nRT. Now rho G and rho G in the bracket is the same, so we can factorize to get rho G as H1 over 2. So bear in mind that this SH1 over 2 is the volumes of these air columns, and this SH1 is the volumes of these air columns. Therefore, we have this equations number 2, which is H plus half of H1 times rho Gs times H1 over 2 equal to m prime m RT. The symbol T's in the equation 1 and equations 2 are the same because we assume the temperature is unchanged when we open and close the valve. Now, if we take the equation 1 to divide by equations 2, then at the right hand side of the equality sign, we see that this MRT and MRT are cancelled out. So we have this M over M prime. This is the ratio that we want to find, the ratio of the mass in air columns before and after the valve being opened. Now it is equal to, now we look at this part and this part. So this rho GSH1 and rho GSH1 will be cancelled. And this is 1 divided by this half, you get 2 here. And the bracket H plus 3H1 over 2 now is divided by H plus H1 over 2. So we have these things here. And if we simplify all these things at the right hand side of the equality sign, we'll get 4H plus 6H1 divided by 2H plus H1. This is the answer we want in terms of H1 and H. The ratio of the mass of air in air columns M over M prime in terms of the H1 and H. Now if we look at this, we can see that this 4H, the first terms in the numerator, is larger than 2H in the first term of denominator. And for the second terms, this 6H1 also is bigger than H1. So we know that this numerator is larger than this denominator. That's why this ratio M over M prime is larger than 1. So the mass before the valve is opened, the gas is released is larger than the mass of the air columns after some mass is released by opening the valve. So from here we can know that M, the ratio of M over M primes is larger than 1.